Hello there, this is your teacher once again, Hamza, right here. And my name is Hamza Rugwama, and today I'm going to take you through a concept called mechanics. And this time around, I'm going to look at what we call equilibrium of forces, which are actually only three acting on a system or on a body. The reason why I have my mask is to remind you to put on your mask every time you have to either be out in public or be somewhere where there are so many people that you don't stay with. Also to remind you to keep yourselves sanitized all the time. You sanitize when you're leaving your home, sanitize when you're coming back, sanitize when you're having public means or public access to where other people also have access. So today's lesson, we're basically going to look at equilibrium of forces, but these forces are going to be three forces. And these three forces, we are going to use what we call the Lamli's theorem. So we have equilibrium of forces, and we're going to have what we call the Lamli's theorem. When a force is in equilibrium, forces are in equilibrium if and only if the resultant force acting on these bodies is zero, or if forces acting on one side of the body can be counterbalanced with the forces acting on the other side. For example, if I have myself saying that I'm in equilibrium, then the force acting on this hand and the force acting on this hand should be equal. But if I'm like this and something is pulling me this side, then I'm not at equilibrium. Equilibrium means in most cases things have to be stable. If I'm being pulled by this other side, then I will not be stable, so I will not be having equilibrium. But if I'm pulled both sides, and as long as my hands are not plucked off, then I will be balancing my body by the force pulling me this side and the force pulling me this side. So one can be in position to even oscillate like this. And there you say we are in what we call limiting equilibrium. But to start with, today we want to derive the expression which we can use in what we call the Lamli's theorem, whereby if you have three forces, for example, one force acting that way, another force acting this way, another force acting here, with these forces being P, Q, R, at an angle theta, an angle alpha, and at an angle beta. So the three forces, as you can see, they subtend some angles to each other. And with that, we shall have some of these sketches done. For example, I can extract out the force and I start with sketching. I can start with sketching, let me start by sketching the P. Then when I sketch the P, I can follow it with the R. This is R. Then I can follow this with the Q. So this is where my Q is. So with that, I have sketched what we call an appropriate triangle of forces. How is it appropriate? It's appropriate in a way that all the forces now are following each other. So they are in a closed system. Okay? So, just like I said, in a closed system, the equilibrium of forces acting on a system or acting on a body predicts that the resultant force acting on those bodies the resultant force acting on that system should be zero. Now, take a keen look here. The angle subtended between the angle between P and Q is theta. So look here. Where is P and Q? P is here, Q is right here. So the angle we subtend here is what? Is theta. So it means the angle inside here, because of angles in a straight line, that angle is 180 minus theta. Then when you come to P and R, the angle subtended, if I prolong the R, and the angle between P and R is alpha, then the angle they subtend out here is 180 minus alpha. So where is my R? My R is right here. If this is my P, and if I look at, this is my P, this is my alpha, and I'll have this, then the angle between R, let me first deal with R and Q. Where is R and Q? R and Q, they're right here. This is the point which predicts them. So the angle here is beta. So it means inside here we have 180 minus beta. Then lastly we have R and P. R and P, if you look at them, they're like this, with this angle as alpha. So the inside angle will be 180 minus alpha. If you have been following some of my lessons and my videos on my channel, don't forget to always go to my YouTube channel and subscribe, and also if possible you can like and share it to all other platforms so that other learners in the world can have such knowledge of mathematics and physics. We can have to use, you can borrow an idea of the sine rule. Remember, sine rule says A over sine capital A is equal to B over sine capital B is equal to small c over sine capital C. So if I have my sides as the forces themselves, then I'll have Q out of sine. The angle opposite to Q is 180 minus alpha is equal to P. The angle opposite to P, where is P? P is here. The opposite angle is 180 minus beta is equal to R, and the angle opposite to R is 180 minus theta. But we take the sine of those angles. So we shall have to remind ourselves about the trigonometry. Sine of an angle, which is 180 minus an angle, is the same as sine of that very angle. So for example, sine of 180 minus 30, i.e. sine of 180 minus 30, this is the same as sine of 150, and it's the same as sine of 30 itself. So sine of 30 is the angle there. So it means sine of 180 minus alpha is the same as sine of alpha. Sine of 180 minus beta is the same as sine of beta. Sine of 180 minus theta is the same as sine of theta. From that, we can extract out this and have Q over sine of alpha is equal to P out of sine of beta is equal to R out of sine of theta. And this is what we call the Lamda theorem. Other books you can find someone saying sine alpha over Q is equal to sine of beta over P is equal to sine of theta over R. These are the same expressions. They will give you the same result. Now what does this call for? It calls for, if you recall, the opposite angle to Q was alpha. So Lamda's theorem says the force you have out of sine of the angle opposite to that force is equal to another force divided by sine of the angle opposite to that force. This angle had theta is equal to another force sine of the angle of opposite to that force. So in case you have different three forces and you know their angles, then you can use Lamda's theorem to always find the solutions of the angles. For example, they can ask you for the angles they subtend. They can also ask you for the magnitudes of the forces. For example, if I had to take a look on this, I'll have example. Find the unknowns in the diagram below. Find the unknowns in the diagram below. So if this is 90 and this is 5 newtons, this can be 6 newtons, this can be 2 newtons, this can be this is 150, and then this can be, if this is we assume this is what, this is 150, then this one can be alpha. So from Lamda's theorem, we are requested to find Q and alpha. So I will say the force is 5 out of the sine of the opposite angle, which is sine of alpha, is equal to 6 out of the opposite angle to 6, which is sine of 150, is equal to 2 out of sine of 90. Recall this symbol implies 90 degrees. Now, the first unknown is alpha. And this alpha can be attained using the concept of total angle sum of the angles in a circular path, which is 360 degrees. So if I have 90 plus 150, I'll get 240. So 240 minus 360, I'll confirm alpha as 360 minus 240, which will give me 120 degrees. So I found alpha. Now, using Lamli's theorem to find Q, I'll have Q over 1, because sine of 90 is 1, is equal to 6 out of sine of 150. You decide to choose only one. You choose one of the ratios. I can use this one and this one. If I've known 120, then I use this one and 120. Any of your choice, any pair. So making Q the subject, Q will give me 6 divided by sine of 150 is a half, and this will give me 6 times 2, and thus my Q is 12 newtons. With that, you are using what we call the Lamli's theorem. It's not restricted to only Lamli. One can also decide to resolve. You resolve the Q to the horizontal and to the vertical. Then you consider sum of upward forces and sum of downward forces is equal to the resultant force is 0. So if I use method 2, if someone had not wanted to use Lamli, method 2, sum of forces in the horizontal, I resolve, for example, I extract out a 90 from here, the balance here will be 60. So I play with the 60 going to the vertical, which is Q cos 60. I've compressed the 60. Then this will be a negative Q sine 60. So along the x-axis, I will have 5 is positive minus Q sine of 60. And then I'll have sum of forces in the y, I'll have Q cos of 60 minus, this is acting in the negative y, minus 6. But because the resultant force is 0, because I said at equilibrium, if the system was in equilibrium, and they told you to find the unknowns below, yeah? Given the system is in equilibrium, maybe I missed this statement, then we say the resultant force has to be 0. Remember I said if this hand is pulling me this side and this one is pulling me this side and I'm stationary, then I'm at equilibrium. So forces this way are equal to forces that way. Or the algebraic sum of this force and this force is 0. It implies when I get the sum of forces in the x-axis, they should give me 0. Sum of forces in the y-axis also they should give me 0. Okay? So in that regard I can use any of them or one of them, and I'll have Q, for example, Q cos theta is equal to 6. Okay? Cos of 60 is a half. So Q times a half is equal to 6, and I'll have Q as 6 times 2, and still I'll get the answer as 12. Okay? So with this regard, in case someone has just resolved, they can also still get the same one solution. So depending on the question. So I just chipped in this so that I can show you that the question is not only restricted to Lamli, but sometimes if you know Lamli, then the question is quite cheaper and easier to handle. Let's have another illustration on this so that we can have an applicable question. So we can have question we can have says a particle of weight 8 newtons is attached to the point B of a light inextensible string AB. It hangs in equilibrium. You hear the statement? It hangs in equilibrium with point A fixed and AB at an angle of 30 degrees to the downward vertical. A force, capital F, at B, acting at the right side to AB, keeps the particle in equilibrium. Find the magnitude of F and tension in the string. So here we are. Sometimes if it's not a string, they can give you a rod. The rod is vertical, then I pull it this way. You see, it will make an angle to the vertical. The vertical is here, so it makes an angle down here. So there is a force pulling it horizontally. So they have said a particle of weight, 8 newtons, is attached to a string. Now, if I consider, some of you might not know what a string looks like. For example, if you consider this this rubber band to be your string, then we can have something simple to illustrate with here. You have something simple to illustrate with. This can be the particle. So if we assume that this is hanging vertically and then we put it aside slowly like this, yeah, by horizontal force, then this is how it's going to look like. Initially it was here. We have attached a particle of weight 8 newtons. It's pulled horizontally by a force capital F. It obtains an angle of, so we have fixed it at A. Here at B is where it has been attached to a particle. A particle of weight 8 newtons is attached to a point B of the lightly extensible string. This is point B. It hangs in the equilibrium with the position A fixed. AB is at an angle of 30 to the downward vertical. This is 30 degrees, making this angle also what? 30. And this is 90. So the total angle sum here will be 100 what? 20. This one is going to be 90. We don't know this angle, we can find it. So ideally, we have the tension in the string, pulling it upwards. This is the tension. The tension is right here in the string. We are pulling the mass this way. This mass has its own weight acting vertically downwards. So we extract out the 3 forces to show that we have the tension, we have the force capital F, and lastly we have the weight of the body, 8 newtons. So to show you how brief Lamli can handle this, this is 90, we have seen this is 120. Then the balance is, this is 210, the balance is 150, which is 270 plus 90, giving you 360 degrees. Lamli's theorem states that T out of sine of the opposite angle, which is 90, is equal to F out of sine of the opposite angle to F, which is 150, is equal to 8 out of sine of the opposite angle to 8, which is 120. We use any 2 ratios, but first look at the ratio which has everything, the force and the angle. Then you can now make F be equated to that ratio, then also make this one of the T to be equated to that ratio. So to start with, F over sine of 150 is a half, is equal to 8 over root 3 over 2. Sine of 120 is 0.866 if you press your calc, which is root 3 over 2. I can divide off the 2's and I'll have F is equal to 8 root 3 over 3 newtons. You can press the calc to get the decimal answer you want. Then if I consider t out of 1, because 1 is coming from sine of 90, is going to be equal to 8 out of sine 120, which is root 3 over 2. Definitely t would be 16 over root 3. This is the same as 16 over 3 root 3 newtons when you rationalize. Now, like I said, Lami is not the end of the world. If you do not comfortable with Lami, then go for equilibrium of forces, which is coming from resolution of forces by resolving. If you resolve, method 2, method of resolving, horizontally, I can resolve because I saw this was 30. So horizontally, this becomes t sine 30, but a negative, where this one becomes t cos 30. So negative t sine 30 shall give me f. Then vertically, positive t cos of 30 shall give me 8. My t will become 8 over root 3 over 2, which is actually 16 over root 3, which is the same answer. Then if I want to get my f, I bring it back here. Actually this f, I should have said f plus. This gives us a 0, so that f becomes t sine of 30, which will give me 16 over root 3 times half. And the answer is 8 over root 3, which still is the same answer, coming to 8 root 3 divided by 3 newtons. So, any one time, if you feel like you want to use Lami, Lami is a shortcut as long as you can reduce the angles very well. If you want to use resolution of forces, you can go to resolution of forces. Now, remember we have discussed today what we call equilibrium of forces, and among the conditions for equilibrium of forces, the resultant force is 0. And today strictly we have discussed Lami's theorem, which is a theorem which deals with equilibrium of only and only 3 forces acting on a system or on a particle. My name is Hamza Rubwama, and I'm still here to always discuss with you or to share with you the concepts of physics and mathematics at all levels. And don't forget to put on your mask every time you're moving out so that you can control the spread of the coronavirus. And then also be in position to always remember to sanitize where need possible. If you don't have an emergency that can let you leave and go out to the public, please stay home and stay safe. Keep practicing. Don't forget to pause in case you need to understand a given concept. And don't forget to reach out to me. My numbers are always shared, 0782 855 674 or 0702 550 946. For those of you who are not in Uganda, you can add a +256 to confirm how you can reach me on my WhatsApp line or on my different social media platforms. With that, I would like to thank God that we are still alive and we are still part of the people who are living, still fighting the coronavirus, the pandemic, and I hope we meet next time when you are still blessed. Have a good day. Thank you.